Hey everyone, in this final video on the introductory part that talked about the review of functions and sets, we're going to talk about graphs and how if we have a general function f of x, what's going to happen when we apply different transformations to this particular function. First of all, we're going to try and we're going to add a particular constant to this function. And let's assume at this point that c has to be greater than 0, that c is positive. Okay. When the function is going to be added to c, what's going to result is the same function. We're going to draw f of x as it is, but it's going to be c units upwards. We'll do a couple of examples in a second to see how these rules will apply. If we were to do this for a negative c, then we would get the exact same result, but the graph would shift downwards by the value of c. So for example, if it's 4, we're going to shift the graph upwards by 4, and in this case downwards by 4. What if we have another particular situation in which inside the argument we add a value a and we subtract a value a, where again a has to be greater than 0, that has to be positive. In this particular case, we're going to get a graph that's going to shift a units to the left. Now this doesn't really seem realistic, like you're adding a to the argument, right? But your graph is shifting to the left. We'll come to see in a second why this is so. And this is going to be the exact same, but the graph is going to shift to the right. Let's do an example now. Suppose we have a function f of x equals x squared. If we were to plot this, probably get something similar to this. Oops. A bell curve. That's what it's known as. So if you apply this transformation to it, the first transformation in this case would be f of x plus c. Let's call c 2. Then we're going to have to find this graph. So it's going to be the exact same graph. The only difference is that it's going to be shifted upwards by 2 units. So now it's going to be starting at the location 0, 2. First, it was starting at the location 0, 0. And if we apply this to fx minus c, we're going to get a graph that starts from minus 2. So basically, now it's going to start from 0, minus 2, which means the graph is going to go something like this. That's the difference between these three graphs. Let's try to apply the same concept for x plus a. And we can assign a value of 2. And what if we want to plot it for f of x minus 2? What would the graph look like then? It's actually very simple. In this particular case, we're going to have to plug in a value of minus 2. If we plug in a value of minus 2, then it's going to give a 0 over here, which means we're going to have to plug in a 0 in the function x squared, which gives us a 0, right? And then we try to plug in a minus 1, we get a 1, which means we're going to get a value of 1 over here. And as we move on and on, if we plug in a value of 0 at this point, we're going to have to plug in 2 over here, which is going to give us 4. So that's how the curve is looking over here. And that's how it is over here. If we were to do this for f of x minus 2, then firstly the curve was supposed to start from here, right? But now it's x minus 2, which means when you plug in a value of 2, then you need to plug in 0 in the function, which means this is going to be 0, and if you plug in a 1, it's going to be minus 1, right? Which is going to be over here basically. And then you start plugging in values which are ahead of 2, right? That's going to be 3, 4, and 5. That's going to give us a curve like that. So it would look something like this. So as you can see, in this particular case, the graph is shifting 2 units to the left. And in this case, it would be shifting 2 units to the right. Let's talk about a few other cases that can be used to draw graphs effectively. We have a function f of x, and we assume that we have a constant c that's greater than 1, as in the previous cases. How would we plot y equals c times f of x? Well, there's not much difference over here. We can see that we'd be stretching the graph vertically if we were to apply this transformation. So stretch the graph vertically by a value of c. And if we were to use another transformation, which is the exact opposite of this, a reciprocal of the function, then we would have to compress the graph vertically by c. Okay? Some other cases include y equals f of c times x. Now, the difference between this case and that is that c is being multiplied inside the argument. So in this particular graph, you'd have to compress the graph horizontally. That's the difference. In that case, you're doing it vertically because the value was being affected by the outside. You could call it an amplitude in this case, and in this case as well. But in this case, it would be referred to as the period, which you guys might have come across when you were studying trigonometric functions. Another example in this regard would be x divided by c. Well, in this case, you would expand or stretch it horizontally in the x direction. Another very important case is when you try to find minus f of x. This would be nothing more than a reflection in the x-axis. So if you have a function over here, something like this, after reflection, minus f of x would simply look something like this. Another situation is when we plug in minus x in the argument. Well, in this case, reflection would occur, but it would be in the y-axis. So, if you have a line that goes from this point to that, it's known as the y equals x line. If we were to use the transformation in this particular case, it would be f of minus x, and the resulting line would be minus x, which is actually this. So this turns out to be a reflection of that line. If you've completed this video, congratulations. You have completed the introductory lectures on functions and sets that we'll be using in later videos to build upon the concepts of Calculus 1. So see you guys in the next video, in which I'm going to be introducing the concept of limits.